Okay, so let's talk about graphs of functions today. And just for fun, let's start out with some domain. And we're going to also introduce range today. So remember, range is just, what y values you have for that function. Let's take a look at f of x equals the square root of x plus 3. Okay, so hopefully you remember what a graph of a radical looks like. Do you remember what that square root graph looks like? What the parent function looks like? It's like that top half of a sideways parabola. You remember that? No? Yes? Okay, let's take a little trip down memory lane. This is what the square root of x looks like. Okay? So then what does the square root of x plus 3 look like? Shifted which way? How about left? How about let's go left? Right? It's locked in, so it's the opposite of what you see. We're gonna revisit all of this soon, okay? But for now, it looks like this. Okay, so this is what our graph of the square root of x plus 3 looks like. Now we know how to find the domain algebraically, I hope, because we've been talking about it, I feel like, non-stop. How do you find the domain of this? What do you have to do? Set it greater than or equal to 0, right? So when we do that, we get x is greater than or equal to -3. Well, if we look at this graph, can't we see that? Right? X is greater than or equal to -3. So I know my domain goes from -3 to infinity. Now, when we think about the range, there's two ways to do it. You can think about the values that you're going to get, like in terms of the answer. If you were to evaluate the square root of x plus 3, what type of solutions would you get? And you can kind of figure out the range that way. Or you can look at the graph. Thinking about the square root, don't we have to get answers of 0 or more, right? They have to be positive answers, but they could be 0. Also, looking at the graph, isn't the lowest point we're at 0, and then we go up to negative or positive infinity? Okay, so in terms of the range, again, you can either look at it graphically or kind of think about those values. So we're going from 0 to infinity there. Okay, so you're going to see ranges introduced now. Everyone okay with that idea? All right, moving on. We're going to talk about increasing, decreasing, and constant parts of the graph. And we're going to write these in interval notation. So we're going to look at these intervals, and then we're going to describe them. Okay, so basically this is a way to describe what is happening to the graph as you move from left to right. Okay, there's an important thing to remember. You're always using open intervals, meaning you're going to always use parentheses for this. When you look at increasing, decreasing, and constant intervals, you're describing the pattern of y using the x values. Okay, so we're looking at the x values here, and we're trying to create these intervals of the graph that are increasing, decreasing, or constant. Okay, so it's pretty easy if you remember the two rules. So this is going to be example 2, and we have to make a quick sketch. So this is going to be pretty rough, but it's all right. Let's put this point at -5, 0. Let's graph this way up here at negative 3, 8. We'll come to 0, 1. We'll call that force negative 6 down here. And 7, 0. Alright, so just make a quick sketch there. It doesn't really have to be to scale. We just want to make sure those points get labeled so we can describe it. Where's everyone today? Okay, so what we're going to do is we're going to talk about the increasing intervals, the decreasing intervals, and the constant intervals. While we're at it, we might as well add in domain and range. Okay, so when you're looking for these intervals, you are reading the graph from left to right, and you're looking at the pattern of y. So you're looking where it's increasing, it has to obviously rise from left to right. Decreasing is falling from left to right, and then constant would be a horizontal line. Okay, so looking at this graph real quickly, everybody agree there's no place where this is constant, right? There's no horizontal lines here, so right now we can write none. Never leave something blank, you know, because otherwise I just think you don't know what it means. Just write none or, you know, something. Write something. Don't leave it blank. Okay, so would you agree that this piece here is increasing? Right, because from left to right, it's rising. All right, so we're just going to kind of color code that. And then, would you also agree from here on, it's increasing? Okay, so this is what we want to describe. We want to describe these intervals. When we do this, we need to make sure that we're using parentheses. So what is the smallest x value where we're starting? Remember, this is going on forever. So what's the smallest x? Negative infinity, right? We're going to imagine this graph goes on forever. So we don't know. We're going to go with negative infinity, okay? Now, moving along, as you go to the left, do you agree that it stops increasing at this point? So that x value is negative 3, and it gets a parenthesis. So you always use parentheses with this. Then it starts back up here at 4. So now this is going to be in union with 4. And then what do we go to? Positive infinity. Okay? Yes?
I don't get starting like going with the infinity, because wouldn't it be really likely to go like up and down and not just increasing the whole time?
Well, we don't know that. All we can see is that. Well, if you plug values into this polynomial function, if you were to plug values in, it wouldn't come back up. We would see that piece. So based on what we see, we have to base our answer. Okay? So now, do you agree that this piece then is decreasing? Everybody okay with that? Okay, so now we start back at negative 3. And we go to positive 4, because that's where it stops decreasing. Notice why I use parentheses. Here I'm saying that it's increasing at negative 3. Here I'm saying it's decreasing at negative 3. If I use brackets, you can't be both increasing or decreasing. This is like that pivotal point where it changes direction. Okay, so that's why we use parentheses for everything. Everybody okay with that? What is the domain? Negative infinity to infinity. What is the range? Now remember, the range is the y. So think about what's going on there. Think about the range. What is it? Same thing, negative infinity to infinity. Some people want to say it's, 8 and negative 6, looking at that. Those are relative max and min points, but those are not the highest and the lowest values, right? We go and we increase without bound and we decrease without bound there. Okay? Everyone all right with this? We're going to try another one of these. I'm going to give you the picture, and then you're going to figure out those pieces. So, let's say I have this graph. 0, 1, 5, 1. And let's do the same thing. So you and your partner talk about those intervals. Make sure you're writing it correctly in interval notation. Bless you. Okay, so take a look at yours compared to mine. So here we saw some constant intervals. We saw those horizontal lines where there's no change in the graph at all. Remember, you're using the pattern of y, but you're describing it with the x values. You're always using those parentheses to describe each interval. If there's more than one, you join them with a union. Did you see here that the range went from -1, which should have a bracket, to positive infinity? Any questions? Because based on what we see, it doesn't go back down. Those arrows say that it increases without bound. Okay, so when we base our answers, it's based on what we see. Okay? All right, can we move on? Everyone okay with increasing, decreasing, and constant? Okay. We're going to talk about even and odd functions. Oh, that's not how you spell even. There we go. Okay, so an even function says that if you have f of x, and you were to take and plug in a negative x, everywhere you saw an x, you would get exactly the same thing that you started with. So whether or not you plug in x or negative x, you'd end up with the same result. Even functions are symmetrical about the y-axis. Okay, and so basically what we're going to do is when you plug in negative x, everything stays the same. Alright, so for example, if you started out with f of x equals x squared, and you want to determine whether or not this function is even or odd, what you would do is you would substitute in negative x. So now I'm going to evaluate f of a negative x. So everywhere I see an x, I plug in negative x, and then I simplify. So a negative x squared is just x squared, right? And now what you do is, once you've simplified, you go back and you compare it to the original. If the original is the exact same thing that you started with, it's an even function. Okay, so this is considered even. These are the same, so it's even. If you think about the graph of x squared, it's a parabola, right? Now, an even function says that it'll be symmetrical about the y-axis. So that means I can take this graph, I can fold it over onto itself if I make that, line of reflection, or that fold line, the y-axis. Everyone agree that's symmetrical about the y-axis? So you can take a look at the graph too to kind of verify your answer. Okay, so that's an even function. Now let's look at an odd function. So an odd function says that if you are to plug in negative x, you'll get out the exact opposite of what you started with. These are symmetrical about the origin. And when you plug in a negative x, everything changes. Okay, so let's take a look at what an odd function would do. Let's say we started out with f of x equals x cubed. If we were to plug in a negative x here, and then cube it, a negative x cubed is like negative x times negative x, which is positive, times a negative x, which is back to a negative. So f of negative x would equal the opposite of x cubed. So once you've simplified, after you've plugged in that negative x, you go back, you compare it. Everyone agree that x cubed and negative x cubed are the opposites? Okay, so because everything has changed, or they're the exact opposite, that makes this an odd function. Now if you were to take a look at the graph here, remember x cubed is an S-curve, right? In order to be symmetrical about the origin, it means that you can rotate it about the origin and it'll map onto itself. So if I was to take this top right side and rotate it, we would see that it would map right back onto that bottom half. Okay, so this is a graph that looks symmetrical about the origin. So we're going to now try this. We're going to try this idea. So we're going to determine if these are even or odd functions. So example 4. Determine if the function is even, odd, or neither. Now keep in mind, not every graph is symmetrical about the y-axis or the origin. So there's going to be cases where there's neither, right? Neither is an option. And then I want you to explain. Okay, so let's start out with f of x equals 3x squared minus 4. Okay, so all you have to do in order to determine if it's even or odd is plug in a negative x, simplify it down, and then compare it to the original. So the notation I'm using function notation. I'm showing the reader I'm plugging in that negative x value. So everywhere I see an x, I now change it to negative x. So that negative x squared is just a positive x squared, multiplying it by 3. I get 3x squared minus 4. There's nothing else I can do, right? So now I go back, I compare it to the original. If it's the exact same, it's even. If it's the exact opposite, it's odd. So what is this? It's even. Now, in terms of an explanation, you could say, when I plugged in negative x, everything stayed the same. You could also use the notation that f of negative x is equal to the original of f of x. Okay? All right, how about f of x equals negative x cubed plus 3x? Okay, so we're going to do the same thing we just did, but we got to be careful when we're plugging it in. We want to make sure we plug it in parentheses. So we're plugging in a negative x. Everywhere we have an x. So I'm going to have the opposite of a negative x cubed plus 3 times negative x. Okay, so when I get this negative x cubed, I get a negative x cubed, right? Once you cube it, you get a negative x cubed, but I have to multiply it by this negative. So here I'm going to have an x cubed minus 3x. Okay, then you go back to the beginning. You compare. What is this? Is it even or odd? Odd because it's the opposite. Everything changed. Every sign changed. So this is odd, and an explanation could be that f of negative x is equal to the opposite of f of x, or when I plugged in a negative x, every sign changed, or I got the exact opposite. You'll write the explanation. You'll be fine. You try this one, and then we're moving on. Okay, so when you plugged in that negative x, you should have seen that 3x squared stayed the same, but 4x changed, right? This became a positive 4x. So half of it stayed the same, half of it changed. This is an example of a neither. It wouldn't be symmetrical about the y-axis or the origin, okay? So if we were to graph this, if you think about what this graph looks like, we wouldn't see any of that symmetry. This is a fine explanation, or putting it in words is fine as well. Everybody okay with even and odd? All right, one more thing. And that's, we got to revisit a piecewise. Okay, so we're going to look at a piecewise functions graph. All right, let's say, well, I guess let's call this example 5. We start out with f of x equals 2x plus 3, where x is less than or equal to 1, and negative x plus 4, where x is greater than 1. Now, I get that these are linear, right? So we could go right into the graph. But I'm going to make a table because sometimes they're not quite as easy. So let's make 2 tables. All right, one is going to be for 2x plus 3, where x is less than or equal to 1. And one's going to be for negative x plus 4, where x is greater than 1. Now, when you do these, you want to pay attention to the domain restriction, but there's going to be a special point that we have to make sure that's on both of our tables. So looking at this 2x plus 3, it's saying where x is less than or equal to 1. So the largest value I should really have on my table is 1, right? Because it can be 1. So I'm going to put a 1 here, but then I'm also going to put a little star next to it because it's important. I'm assuming that you know how to make a table of values. So this is 5, right? Plug in the 1 for x and simplify. So now we want to choose values that are less than 1. So like 0, I get 3, negative 1, I have 1. Good enough, okay? So this is a line. Now, thinking about this graph, this 1, 5, should this be like a closed or an open circle? Closed because of this equal to, right? So I'm just going to make myself a note and put a little closed circle next to it. Now, for the next graph, even though this domain has to be greater than 1, I still have to put 1 on the table. But how do I let the reader know that you cannot have 1 as an option here? Just that open circle. So even though it's not defined in the domain, it still has to go on there because I have to see that gap between these, or maybe that they join at the same point. All right, so 1 is going on here. Again, I'm just kind of marking this to let myself know this is special. If I plug in a 1, I get 3. So here, this is going to be that open circle. So I cannot equal 1, but now I have to choose values that are greater than 1, right? Because x is greater than 1 for that domain. So, you know, maybe like 2 and 3. Okay, now let's go ahead and just graph this. So 1, 5, we're going to have that, oh, I put it at 6. We're going to have that closed circle, 0, 3, negative 1, 1. Okay, so here is this piece. So this is where f of x is equal to 2x plus 3, and x is less than or equal to 1. Ignore this little point here. Now, when I go to 1, 3, I want to make sure that I leave that circle open because that's not within the domain, but 1.000001 is. Okay, so I want to make sure that my graph starts where it's supposed to. Sometimes those points are going to overlap. And we'll see that and you just close that circle in. Okay, so if these were the same, like if this is 1, 5 and this is 1, 5, then you would just overlap them and it would be closed. And this is where f of x is equal to negative x plus 4 and x is greater than 1. Okay?